We have just given the proof of the first fundamental theorem of calculus. So, fundamental theorem of calculus. Can anybody tell me? Does anyone remember what the fundamental theorem of calculus talks about? What is it? What's the idea? What's the purpose? What does it do for you? What does it do?
It helps you find the area under functions by helping you find the antiderivative.
Okay, so sort of, yeah. So it gives you an antiderivative, right? You start off with you start off with a function. You start off with a continuous function, right? And you're looking for some other function whose derivative is this function, right? And it turns out that you can create an antiderivative. So let big F be something. Because I remember here's the real key part, right? So how do we make the antiderivative? How do we make the antiderivative? It turned out that we could make an antiderivative out of the original function, right? A, B. You have some function f, some function little f, and you'd like to make a function whose derivative is little f. And does anyone remember? No?
I have it written down. I can read it off.
You have it written down. Don't read it off. See, I'd like to know if anyone can drag it out of their brains. There's some way of, yeah.
Was it something like little f a minus little f b or something?
Not exactly. So you created this guy that was the integral of little f, right? The definite integral of little f from a to whatever point you're evaluating. Okay, so you create this new function saying we're going to define f at x, right? We're going to define f of x by letting that be the integral from the integral of little f from a to x. Okay, and what we saw last time was that turns out that f is differentiable on AB. And when we took the derivative of it, you remember what happened? You ended up with this limit. You ended up with this limit of 1 over h, the integral from x to x plus h of little f as h goes to 0. Right? And then that limit, as h went to 0, that actually gave you f of x, little f of x. Okay, so this turned into the derivative actually is little f. Okay, so it's possible to create an antiderivative for continuous functions on this closed interval. Okay, that's basically the moral. It's possible to create an antiderivative of a continuous function using the definite integral.
The last f of x there, that's a lowercase f.
That's a lowercase, yeah. Yeah, Emily.
Why didn't bother having an x besides a and b? Can't you just make it xb?
I'm not following. I'm not following. What's x?
X, so on the graph,
Here?
that x, can't x just equal b and then it would just work like that? If you just make your x equal to b,
I'm not,
so then it's just a whole.
thank you. So, yeah, so
you're trying to make it closer.
You're trying to make an antiderivative of little f.
Right.
Okay. So you get the setting here, right? You've got this function little f. You got this function little f, you're trying to make a function whose derivative is little f.
Yeah.
Okay, and how you do it is, say, you create this guy, big F. Big F is defined as the integral of little f from a to x. Okay, so big F is actually this area. If I said, what's big F of a? Big F of a would be the integral. Big F of a would be, what would big F of a be?
Yeah.
It would be 0, right? Because you're integrating from a to a. Okay, if I'm saying what's big F of b? Big F of b is the integral from a to b. Right? Big F of b would be this area. Okay, and what we saw last time, what we saw at the end of class last time was that if you create this function big F, which is the area of little f, then it's actually an antiderivative of little f. Okay, so that was the main thing. So I hope if you watched the video, if you weren't able to come here last time. Yeah, Rachel?
Can you do a really quick example of how you actually find f of x using that?
That's it.
The big F.
You just leave it like that. That's it. That's it right there. So for example,
But to evaluate that, you need to know what big F is. Don't you?
No, because you have the little f of x function.
But like to evaluate that, that's equal to big F of a, big F of x minus big F of a, isn't it? So how do you actually find?
no, actually, no. You're sort of getting confused between. I think you're getting confused. So you're saying that, well, if I actually want to evaluate the integral of, if I want to evaluate, so yeah. So I think what you're saying is that if I want to evaluate an integral of little f, say from a to b. Right. Then I actually need to know what big F is.
Yeah.
Yeah. Well, that's sort of not the point. That's not the point of this thing.
The point is that we know. Okay.
The point is simply that you can construct this antiderivative. Okay. So not because so if you tried to use this to evaluate an integral, it would simply say you get the integral. It would say this is equal to itself. Okay. But you don't use this to you're not using this to evaluate something. It's rather you're using this to get an antiderivative. So the point is simply you can get an antiderivative. A function. If you're looking for an antiderivative of a function, you can get it by doing this. Yeah. Okay. So that's fundamental theorem of calculus 1. Let's see how fundamental theorem of calculus 2 comes out of it. So, fundamental theorem of calculus 1 gives you another way of getting fundamental theorem of calculus 2. Okay. So remember what fundamental theorem of calculus 2 said. It said that if f is continuous on AB. And let me write it like this. G is any antiderivative of f on AB. Then the integral from a to b of little f is just the difference of the antiderivative at the endpoints. Right? That's the fundamental theorem of calculus 2. Right? Everyone remember that? Okay. And here's the proof. The proof is sort of funny. Okay. You say, well, look, let f of x be this guy that we created over here. The antiderivative of little f from fundamental theorem of calculus 1. So this is we're saying that you can, for any antiderivative, the integral is going to be the difference at the endpoints. Okay. So now let's look in the proof. Let's say, well, let's just look at one antiderivative. Okay, here it is. So what's f of b minus f of a for this guy, for this one antiderivative? Think for half a minute, and then tell me what this is. F of b minus f of a equals what? Some of you are looking at me. Don't look at me. I have no answers on my face, I think. Oh, I don't know. Maybe looking at me helps you? I'm not sure. Can you talk to each other for half a minute? To say, well, it turns out to be. Okay. Anyone wanna tell me what, if f of x is this thing, the integral from a to x, what's f of b minus f of a? Who would like to tell me? First off, what's f of a? Maya?
Isn't it 0?
F of a is 0, right? Because you're taking the integral from a to a, so it's 0. What's f of b? Maya?
The integral from a to b of little f.
The integral from a to b of little f. Okay. So the integral from a to b of little f. Okay. So what we're noticing is that if you look at this one antiderivative, then it's different at the endpoints, gives you what you want. Okay? For this one antiderivative. Okay? But what the theorem said was that for any antiderivative, the difference at the endpoints is going to give you what you want. Okay? So why is it true for any antiderivative that the difference at the endpoints is going to? We've only seen it for this one antiderivative. Okay, two bonus points on the final if somebody can get it in the next minute and figure it out. Why is it true that for any antiderivative this is going to happen? We've only shown it for this one guy.
Well, I've been saying maybe because I want to give you credit. Maybe because the fundamental theorem of calculus 1 that says that f prime of x equals f of x.
That's what we're using here. Kyla?
Because the antiderivatives only vary by constant.
Emily?
I mean, just if big F of b minus big F of a is changing y, and then you divide that by dx. That's the split, which is.
Ellie?
Is it because the fundamental theorem of calculus 1 says that defines any antiderivative?
No, fundamental theorem of calculus just says that this is one of the antiderivatives, not that all of them look like this. Yeah, if the fundamental theorem of calculus said all antiderivatives look like this, then that would do it for you. But what Kylie and Rachel are noticing is that if G is also any antiderivative of big F, then G minus F must be some constant, right? Must be some constant, right? Sharon, did you have it?
What?
Did you have it?
She just dropped her pen completely.
Oh, okay. Okay, just drop your pen. I'm not going to give you points for that. Okay, right? And so, right, so then G of B minus G of A is going to be F of B plus C, right? So G is then F of X, G of X is F of X plus C, so you get F of B plus C minus F of A plus C, and the constants cancel out, and you get F of B minus F of A again. Right? And we just saw that F of B minus F of A is the integral from A to B of little f. Okay? Great. So I'll give both of you points. When did people start high-fiving each other? It's kind of interesting. My children, I think I said high-five each other. My daughter, started when maybe she was 6 and he was 3. Like, Taka, high-five. Okay, great. So you see how the fundamental theorem of calculus, part 2, the one that's useful to you, right? Comes out of fundamental theorem of calculus 1, this sort of theoretical thing that says you can always make an antiderivative in this way, right? That this thing is an antiderivative, and then fundamental theorem of calculus 2 says, okay, that gives us that when you have any antiderivative, then its difference at the endpoints is going to be the integral of the function whose antiderivative you are. Okay. Everyone okay? Please, everyone see that? So this is right, and you see that this uses this fact that any functions who have the same derivative differ by a constant. You remember where that came from? That came from the mean value theorem, right? That was a consequence of the mean value theorem. So again, the mean value theorem is behind everything. Okay. Okay. So so fundamental theorem of calculus, right? It says that if you create this function like this, then its derivative is the integrand, right? So, okay. So if I write something like, if I write the integral from a to x of the square root of 1 minus t squared dt. Okay, and I say, I'd like you to differentiate that with respect to x. Right. Then you say, oh, that's easy. Well, by the fundamental theorem of calculus, this is just the integral from a to x of some continuous function, and so this is all this is going to be the integrand.
Do you need your x to be a t?
No, I don't actually. No, I don't, because
Oh, right, you put it in
yeah, this is a so this thing here is some function of x, right? And the question is, what's the derivative? What's the derivative of that function? Well, it will be 1 minus x squared. So yeah, don't worry, people make that mistake. This thing here is not a function of t. T is the dummy variable, just saying you're going to integrate something from a to x, and you can call it whatever you wanted, right? This t doesn't really matter. You can replace it by, I could replace it by bananas. You could replace it by Chinese symbols. It doesn't matter, right? Okay, it's just saying you're going to integrate something between a and x, over this interval. Okay, so right, you see how you can actually now differentiate these things, which probably would have been pretty boggling for you to differentiate before. Right? If I said differentiate this 2 days ago, then it would have been impossible. But now you can differentiate this sort of function. Right? If I say, simpler, if I say differentiate, if I say differentiate this, what's the derivative? Cosine x? Cosine x. Right? It's just going to be this is the antiderivative of cosine, so it's the derivative of the antiderivative, it's just going to be the cosine. Right? Fundamental theorem of calculus says this is an antiderivative of the cosine, so its derivative is cosine. Okay, you can combine this with the chain rule. So what combining with the chain rule? If I say f of x is the integral from a to x of f of t dt, and I put something. Suppose I look at f of u of x, okay, and I want to differentiate that. What's f of u of x? Well, by the chain rule, this is going to be f prime at u of x, u prime x, right? But f prime is little f. So you get little f, you get the integrand evaluated at u of x times u prime x. Okay, so if I go back to this thing over here, and I say, what's the derivative of cosine t dt? The integral of that from a to x squared. What's the derivative of that from a to x squared? Well, I know this is going to be the derivative of the function, that's the integrand, that's cosine, evaluated at u of x times the derivative of u of x. Right? Right? If I put in any function up here, u of x, cosine x, dt, and I say, what's the derivative of this thing with respect to x? Well, that's just going to be cosine of u of x, u prime x. Right? In particular, I've got an x squared there. I'm going to end up with cosine x squared times the derivative of x squared. Okay, so this is all this is the chain rule combined with the first fundamental theorem of calculus. Questions? Any questions? Well, let me do an example first. Do an exercise first. Okay. So some exercises. First, the derivative from a sine x of square root of 1 minus t squared dt. Okay, turn to somebody else, say what you got. Okay, who would like to say what they got? Which got? Yep. Okay. Just take the integrand, right? You take the derivative of this function, evaluate the sine of x, right? The derivative of the function is going to be the integrand, so you can take the integrand, evaluate the sine of x, times the derivative of u. Yeah, Rachel.
What if the bottom bound is an a?
Isn't it constant?
Yeah.
Like it's some value or something? It's some other function?
Yeah.
Sure, we'll get to that in a second. So, second example, which leads up to that. Suppose we do the opposite, say a sine x L minus t squared dt. Oh, what's that? You should be able to tell me immediately, Liza.
Just negative.
It's just negative the previous, right? Because you know that this thing here is this thing in the this thing in the parentheses is just negative this thing, right? We had that earlier, but the integral from a to b is negative the integral from b to a, right? So if you switch the order, then you just introduce a negative sign, right? So all this is the derivative of negative the integral from a to sine x L minus t squared dt. Right, so that's going to be negative what we had before. Okay. Third example. What if you have something like the derivative of something like this, the derivative of cosine x to sine x of the integral of 1 minus t squared dt from cosine x to sine x. Okay. So in this case, the trick is that you introduce a third point. Okay, you introduce a third point. You say, I'm going to call this the integral from cosine to a of plus the integral from a to c. Okay, right? Because this integral here, again, so here we're using those simple properties of the definite integral that I mocked, but they're coming in handy here. Right? And so this is going to be it's going to be negative the square root of 1 minus cosine squared times negative sine squared, negative sine, plus the square root of 1 minus sine squared cosine x. Okay. Okay. Anyone confused by that? Anyone have questions? Okay. All it is you're combining fundamental theorem of calculus 1 with the chain rule. Right? Combining with the chain rule, and then adding those basic properties of definite integrals into the mix to extend your reach, extend the reach of this technique. Okay. Okay. Okay, I think that's where we're going to stop for today.